Hey everyone, it's me again with another episode of Physiology 2, again, especially for you. In this video, it will be about chemistry, but officially it will be about respiration. So if you still need to refresh some of your high school chemistry, then please do that before playing this video. So respiration is all about the gas exchange, as we've explained before. So in this video, our focus is going to be on the actual exchange of O2 and CO2 through the gases. And that is where the respiration really gets into the real chemistry. So to get started, I have this video for you that is roughly about 2 minutes. I'm just going to play it completely, and then I'll explain everything else.
Fresh air entering the lung carries oxygen with a PO2 of 160. The presence of moisture in the lung results in reduction of the PO2 to 104. Fresh air entering the lung carries carbon dioxide with a pCO2 of 0.3. The carbon dioxide delivered to the lung from the blood raises the pCO2 to 40. At the arterial ends of the pulmonary capillaries, oxygen diffuses from the air in the alveoli into the blood, and carbon dioxide diffuses from the blood into the alveoli because of differences in partial pressures. As a result of diffusion, at the venous ends of the pulmonary capillaries, the PO2 in the blood is equal to the PO2 in the alveoli, and the pCO2 in the blood is equal to the pCO2 in the alveoli. With no differences in partial pressure, there is no more net movement of oxygen or carbon dioxide. Oxygen diffuses out of the arterial ends of tissue capillaries into the tissue fluid, then into the cells, and carbon dioxide diffuses out of the cells into the tissue fluid, then into the blood because of differences in partial pressures. At the venous ends of tissue capillaries, the PO2 in the blood is equal to the PO2 in the tissue fluid, and the pCO2 in the blood is equal to the pCO2 in the tissue fluid, resulting in no more net movement of oxygen or carbon dioxide. The blood now carries the oxygen and carbon dioxide to the lungs. In the body, all of these exchanges occur simultaneously.
All right, so that was this video, and I think it's a great video because it's a very clear animation of the entire process. So if this video already made sense to you, you can skip definitely some parts of this video. But in the next slides, I'm gonna break down the different components and the explanations that you found in this video. So it's all about pressure and partial pressures and pressure differences, etc. So what is important is that if you look at a closed system, a closed volume, then the different partial pressures simply add up to the total pressure in case you have a gas mixture, and that is what's called Dalton's law. So in a normal situation, on a beautiful day, it might be a little bit more, but definitely a relatively normal sea level atmospheric pressure is 760 milliliters of mercury, millimeters of mercury, sorry. And then you can see that out of this total pressure, roughly about 80% is nitrogen, around 21% is oxygen, and CO2 is almost zero. So that makes up a total of 100%. And if you add up these individual pressures, you will get again to this 760 as the average for this example. So in order for gas to flow inside the body, we need a pressure difference. And then the gases will simply flow from high pressure to low pressure. So you need to create this pressure differential, and the speed then depends on this differential, but also on the solubility of the gas in the fluid. And an example of that you will see later in this video, and definitely we will follow up on saturation in the next video. So it's all about pressure differences and the differential from high to low. The solubility of CO2 in water or blood is 25 times more than O2. And both CO2 and O2 are a lot more soluble than nitrogen. So at normal sea level physiology, therefore, we will not focus on nitrogen because that is something that will go into the body and out of the body. Only if you're interested in scuba diving, for example, nitrogen definitely could play a role. But here we're focusing only on CO2 and O2. Again, this is a table where I could say, please know your numbers. So for PO2 and PCO2, this table clearly shows you the different partial pressures. For example, for venous pressure, for arterial pressure, for alveoli pressure, and for atmospheric pressure. Now, for example, here is a pressure difference between the atmosphere and the alveoli, which will explain that air in that situation will flow from the atmosphere into the alveoli. More importantly, you see that there's still, although smaller, a pressure difference between the alveoli and the arterial blood in regards to PO2. So this relatively small pressure difference is still enough for air to diffuse from the alveoli, or for O2 to diffuse from the alveoli into the arteries, into the capillaries of the lungs. For PCO2, you see that the pressure difference is the opposite. So here you have in the arterial blood surrounding the capillaries, for example, you have 40 millimeters of mercury pressure, and in the alveoli it's also 40, so that is only a marginal difference. And then in the atmosphere, as we saw in one of the previous slides, it's 0. So it is always relatively easy for the body to have CO2 diffuse from the alveoli into the atmosphere because the pressure difference is relatively large. In this drawing, you can basically see the same numbers but then visualized in the actual circulation. So please have a look and see if you can follow the whole circulation and see what the logic is of all these numbers changing, and that makes it a lot easier for you to also remember those numbers. This is an interesting image from another book, the book of McCardle, that is also on the recommended list, where you see the actual cascade of oxygen and the partial pressure of oxygen dropping from atmosphere to alveoli, to arteries, to capillaries, and then finally to the muscle cells. So you see how the different pressures lower as you get closer to the actual site, the mitochondria, where the oxygen is actually used to have it converted to ATP. Now, if you look at this figure, you can see the connection between the actual partial pressure in the alveoli and the ventilation. So to what extent has a change in ventilation an effect on the pressures? Well, what you can see here in the green graph is that if you upgrade the alveolar ventilation, then as a result, the alveolar pressure of CO2 will drop. If the alveolar ventilation will decrease, the alveolar partial pressure will go up, and basically the opposite happens for O2. And these points represent the normal values, so from there, slightly increase or a slight lowering in minute ventilation will have a direct effect on the partial pressure inside the alveoli. So if you look at the abnormal situation, then you can see that sometimes the actual gas exchange and the diffusion is impaired. And that could be done, for example, by a thicker membrane. In the earlier videos, I showed you that the membrane is usually very, very thin, but in some pathologies, for example, that membrane can be thickened, which will cause an extra barrier for the gas molecules for diffusion. So that can make the process a lot slower. But also a reduction in the total surface area. And remember the size of a tennis court as the metaphor for the entire surface of a normal healthy lung. Well, if that reduction is significant, then definitely diffusion can also be affected. So that's two examples of how a pathology can actually influence diffusion. And in this graph from Vander, you can actually see very nicely the difference in the diffusion and how much of the actual capillary length is normally used and how much of that is used in a abnormal situation where diffusion is impaired. If we look at the green line first, then you can see that basically after roughly 30% of the capillary length, so had the blood passing through the or along the alveoli, already after 30% of that length, maximum PO2 is reached, and any further flow of blood is not really upgrading that at all. So this shows again that in a normal situation, diffusion is never going to be a limiting factor because you have an overcapacity. In a diseased situation, for example, when the membrane is thickened, what you can see here is that it takes a lot more time for the diffusion to reach the right levels and for the PO2 to reach the levels that you want it to be at, close to 100 at least. So here you can see that it does look like the capillary length is not enough because the diffusion is relatively slow and you will not reach the actual same PO2 in the pulmonary capillaries compared to a healthy person. So then we can make the step towards the actual transport. And this is also the first step towards the topic of saturation, which will be covered in the next video in more detail. But there's actually two mechanisms for O2 transport inside the blood. The first one is to just have O2 dissolved into the blood, into the water. And the other method is to have it combined with hemoglobin. Now, if you look at the numbers, then you can see that definitely the amount that is free is relatively small. So what these numbers show you is that from each liter of blood, there's only a small fraction of O2 dissolved. And although the numbers are small, it is very important to realize is that the amount of free molecules of O2 are the determinant of the PO2, of the partial pressure. So not the amount of O2 that is bound to hemoglobin, as we will see later, but really the free amount of O2 molecules. So with these small numbers, still the significance is there. But as you may know already, the most important factor in the binding of oxygen inside the blood are the red blood cells, the erythrocytes, because they contain hemoglobin, and hemoglobin is actually where the O2 can bind to. And the chemical picture of the hemoglobin is visualized right here. And the most important thing to realize is that because of an iron molecule, O2 actually has a binding place. So iron is essential for the O2 to bind. And within each hemoglobin molecule, you actually have 4 iron atoms that can actually act as a binding place. And in contrast, for example, we will see later that myoglobin is quite similar. So you consider that maybe the little brother of hemoglobin. Myoglobin that's present in the muscle cells only has 1 iron molecule. But iron is therefore the most essential part because that forms the binding place. So how does it work? Well, in this video, you can see very nicely how adding hemoglobin to a bowl of water can actually cause the amount to really increase compared to just the free molecules, but you still have the free molecules left to determine the pressure. So let me play this video for you. So what you can see right here is that basically in both chambers, O2 can diffuse freely. Now, here we're going to add hemoglobin to one side, and then you can see that the pressure lowers on the right side temporarily, and as a result, this pressure difference will cause O2 from part A to diffuse into part B. So right now in part B, you have a lot more O2 molecules in total, but you still have the same O2 pressure on both sides, and that is what causes then the responses and the diffusion and all the other factors. So PO2 is really essential, but for the total capacity, hemoglobin is essential. And in this picture, you can see that also in a static image. So this is the final situation, but we started with this one where we have molecules that are able to diffuse freely through this membrane, and then the pressure on both sides of the membrane is equal. As soon as you start adding hemoglobin, you're basically lowering the partial pressure on this side because the free molecules will actually go down and bind to hemoglobin. And because of the pressure difference here, you will have diffusion from A to B, and ultimately there is then again a equal amount of partial pressure on both sides, and the amount of free molecules is still there to determine the partial pressure. To summarize, here you can see the table that shows you the different numbers. So the amount of free is only 3 milliliters per each liter. The amount of O2 bound to hemoglobin is 197. Altogether, if you look at a cardiac output of 5 liters per minute, you can see that your body now has the capacity to transport roughly 1 liter of O2 each minute based on this cardiac output of 5 liters. Well, to finish it up, 2 slides that will give you the numbers. First of all, the volume. Here you can see the whole circulation where you see the volumes of O2 here on the left. And here you can see the volumes of CO2 on the right. Have a look at those numbers and see if they now really make sense. And in this slide, a very similar overview, but now again with the actual partial pressure values for PO2 all the way to PO2 right here, and the same for CO2 all the way from here to there. And that was it. So thanks again for watching this video. I hope you like it. Please let me know if you have any questions, and I really hope to see you soon in the next video.